this lesson we're going to talk about rates, and you see right there in the vocab section, a rate is a ratio, aka fraction, that indicates how two quantities change with respect to each other, which sometimes the official, like mathematical definition doesn't really click with us until we see it in practice. So if we spend $200 in 4 days, and I divide that out, 4 goes into 250 times, so you spend an average of $50 per day. Please note that that per is where the fraction bar goes. Also note that whatever unit is mentioned first is what goes on top, and then when we get it to the per, we're talking about the bottom number actually being a 1. Per day means $50 in each and every one single day. Just to say it a bunch of different ways at the same time. All right, so how do we do this? The national debt, here's our first example, was $15 billion in 2011 and $19 billion in 2016. Find the average rate at which the debt was increasing. All right, I'm gonna I gotta come clean and tell you I don't know where these numbers exactly came from. I rounded these to nice numbers from your textbook. So your text printed them. I guess I can't verify it is what I'm trying to say. All right, so how much did it increase? Well, it went from 15 billion all the way up to 19 billion. So it definitely is increasing. It went up $4 billion. And it went from 2016 to 2011. So think about how many years that is. That is 5 years. So $4 billion in 5 years. Or if I actually do that math real quick, I'm going to type this into my calculator. 4 billion looks like this. Divide by 5. You can hear me punching those keys. So I've got 8, and then I have 0, 0. So I have 800 million. I don't need to write that out per day, or per year, sorry. Or you could write it like this, 800 million. No reason to write all those zeros. Not quite sure why I chose to, per year. Lots of different ways to say the same thing. And we're talking about money here, so just be really careful with your units. As you're working out the problem, I'm not sure you need to add units to every little section. You get to do your own notes there. All right, let's look at our next example. On May 5th, the odometer on the car read 25,375 miles. On May 11th, so 6 days later, the odometer read 32,255. Find the average rate of miles per day. So this one might be a little more clear. Miles per day means that we definitely want to have the miles on top, days on the bottom. And so what was the change in the number of miles? Well, we ended at this number. We started here. So it went up by that amount. we went from the 11th, or from the 5th of May to the 11th of May. So we had a span of 6 total days. So this is 6880 over 6. So this is how many miles we went in 6 days. So if I divide that by 6, it doesn't quite work out nice, so we're going to have to give a decimal approximation. We went about 1,147 miles per day. I rounded it up. It was actually 1146.66667. So I rounded that to the nearest mile. We can also take our rates from a graph. And so you have a couple of options. We can count out the coordinates, or we can just count up and over and figure out the rate of increase here, since we already know how to graph using slope-intercept. So if I go from this point to this point, looks like I went up from 80 to 160. Looks like I went up 80. And I went right from 2 hours to 4 hours. I went right 2 hours. So I went up 80 miles, and I went right 2 hours. So that would reduce down to 40 miles per hour. If you didn't want to look at the graph and count it out, personally, I like that option better if it's possible to do that. I would say, well, gosh, this point right here is the point 2, 80. And this point right here is the point 4, 160. But of course, your book puts this section before that you've learned the slope formula. And so then I would plug that into the slope formula and you would get the same thing. Assuming you cheated and took my advice, not cheated, but took my advice and watched that, you would understand about this slope formula. Here's your x1, y1. Here's your x2, y2. And so you're plugging that into your slope formula, and notice that you're going to get the exact same thing. So whatever way you prefer, you get the same answer. Sometimes it's kind of nice just to count it from the graph, but be careful what the axis are counting by. So in this, it looks like we have some type of leaking tank, and it's leaking gallons. And so it looks like here we're counting by ones. Looks like here we're also counting by ones, so we're going up 1, 2, 3 gallons every 1, 2, 3, 4 minutes. That is a problem. So we're losing 3 gallons every 4 minutes, or we are losing 0.75 dividing 3 by 4 gallons per minute. Feel free to try this one if you'd like. Here we have a problem. I just imported some of these graphs from online, from pictures I saw on the internet. There's others in the online version of your textbook. So here we have 40 cubic feet of air when we are at 0 minutes. So this is kind of our starting point. And here we have no air after 6 minutes. And so again, a nice little reference back to those intercepts. So this one's going down. You can see this line is going down. We are using up air. We are losing air. And so we are going down 40 in 6 minutes. We are going down 40 cubic feet of air in 6 minutes. That doesn't divide perfectly. That's going to be roughly 6.67. So we're losing about 6.67 cubic feet per minute. Depends on the problem on MyMathLab. If you're going to estimate, it will probably tell you how to write the answer, whether they would want that to round or whatnot. But that is how rates look. And I think that probably, yep, that wraps that up. So eventually we do get into the official slope section where it is in the book, and that's coming next. Take care, everyone.